Adjusting transformer primary taps to boost secondary voltage is generally feasible. By changing the connection point in the primary winding, you can increase the output voltage. This adjustment, however, can have some effects on the transformer's operation. Firstly, transformer efficiency might be slightly reduced when boosting the secondary voltage through tap adjustments. Secondly, transformer loading must be considered. Increasing the secondary voltage could reduce the maximum load the transformer can handle before overheating. Regarding the circuit breaker, adjusting the primary taps usually doesn't trip it, assuming the transformer is adequately sized for the load. The utility supply voltage remains within the transformer's normal operating range, and the feeder circuit breaker is rated for the increased secondary voltage. Be cautious of utility supply voltage fluctuations. If the incoming voltage fluctuates significantly, boosting the secondary voltage could cause problems. A fluctuation that raises the utility supply voltage above the transformer's maximum could trip the breaker or damage the transformer. It's essential to consult with a qualified electrician or transformer manufacturer before making any adjustments. They can assess the feasibility, potential implications, and ensure all safety and code requirements are met. When a transformer's primary taps are adjusted to boost the secondary voltage, several factors must be considered to ensure safe and efficient operation. The adjustment process involves changing the tap setting on the primary winding, which alters the turns ratio between the primary and secondary windings, thereby affecting the output voltage. Firstly, understanding transformer taps is crucial. Transformers often have taps on their primary windings to allow for slight adjustments in the input voltage. These taps are typically labeled with voltages above or below the nominal primary voltage. For example, a transformer designed for a 480-volt primary might have taps at 460 volts, 480 volts, and 500 volts. If the incoming voltage is consistently lower than the nominal voltage, adjusting the tap to a lower voltage setting can help maintain the desired secondary voltage. Secondly, when boosting the secondary voltage, it's essential to calculate the new turns ratio and its impact on the output voltage. The turns ratio is the ratio of the number of turns in the primary winding to the number of turns in the secondary winding. Adjusting the primary taps changes this ratio. The formula to determine the secondary voltage is secondary voltage equals primary voltage divided by turns ratio. For instance, if a transformer has a turns ratio of 4:1 and the primary voltage is 208 volts, the secondary voltage would be 52 volts. By adjusting the primary tap, the turns ratio changes, subsequently altering the secondary voltage. Thirdly, efficiency is a critical factor to consider. While boosting the secondary voltage can solve immediate voltage drop issues, it may slightly reduce the transformer's efficiency. Transformers are most efficient when operating near their design voltage and loading conditions. Operating a transformer at a non-optimal tap setting can increase coal losses and copper losses, leading to a decrease in overall efficiency. The efficiency decrease is usually marginal, but it should be considered, especially for large transformers or those operating continuously. Fourthly, transformer loading is another vital aspect. Increasing the secondary voltage may reduce the maximum load that the transformer can handle before overheating. This is because the transformer's kVA rating remains constant. If the voltage increases, the available current decreases, and vice versa. The relationship is kVA equals volts times amps divided by 1000. If the voltage is boosted, the maximum allowable current decreases to maintain the same kVA. Overloading the transformer can lead to overheating, insulation breakdown, and ultimately transformer failure. Fifthly, assessing the feeder circuit breaker is necessary. Adjusting the primary taps will not typically trip the feeder circuit breaker, provided that the transformer is properly sized for the load, the utility supply voltage is within the normal operating range, and the feeder circuit breaker is rated for the increased secondary voltage. However, it is crucial to verify that the circuit breaker's ampacity is sufficient for the new operating conditions. The circuit breaker protects the transformer and connected circuits from overcurrent conditions. If the secondary voltage is increased, The current in the primary winding may also increase, potentially exceeding the circuit breaker's rating if the load remains constant. Sixthly, utility supply voltage fluctuations are a significant concern. If the utility supply voltage is subject to significant fluctuations, adjusting the primary taps to boost the secondary voltage should be done with caution. A voltage fluctuation that raises the utility supply voltage above the transformer's maximum operating voltage could trip the feeder circuit breaker or damage the transformer. For example, if the transformer is set to boost the secondary voltage when the utility voltage is already at the higher end of its tolerance, any further increase in the utility voltage could push the transformer beyond its design limits. Seventhly, monitoring the transformer's temperature is advisable. After adjusting the taps, it is essential to monitor the transformer's temperature to ensure it is operating within safe limits. Overheating can indicate overloading or other issues that need to be addressed. Infrared thermometers or thermal imaging cameras can be used to monitor the temperature of the transformer's core, windings, and other critical components. Regular temperature checks can help identify potential problems before they lead to failure. Eighthly, consulting with a qualified electrician or transformer manufacturer is highly recommended. They can perform a comprehensive assessment of the electrical system, including the transformer, feeder circuit, and connected loads. They can also verify that all safety precautions and code requirements are met. A qualified professional can provide valuable insights and recommendations tailored to the specific situation, ensuring that the tap adjustments are made safely and effectively. Ninthly, documenting all changes is important. Keep a detailed record of all tap adjustments made to the transformer. This documentation should include the date of the adjustment, the tap setting before and after the adjustment, the reason for the adjustment, and any measurements taken, such as voltage and current readings. This documentation will be helpful for future reference and troubleshooting. Tenthly, consider voltage regulation. Adjusting the primary taps to boost the secondary voltage is a one-time fix. It does not address the underlying issue of voltage regulation. If the incoming voltage is consistently low, a better solution may be to install a voltage regulator. Voltage regulators automatically adjust the voltage to maintain a constant output, regardless of fluctuations in the input voltage. This can provide a more stable and reliable power supply for sensitive equipment. 11thly, assess the impact on connected equipment. Before adjusting the transformer taps, it is important to assess the impact on connected equipment. Increasing the voltage may improve the performance of some equipment, such as motors, but it could also damage other equipment that is sensitive to voltage fluctuations. Check the voltage ratings of all connected equipment to ensure they are compatible with the new voltage level. 12thly, follow local codes and standards. All electrical work must comply with local codes and standards. This includes the National Electrical Code (NEC) and any local amendments. Ensure that all tap adjustments are made in accordance with these codes and standards to ensure safety and compliance. 13thly, consider the age and condition of the transformer. Older transformers may be more susceptible to problems when the taps are adjusted. The insulation may be degraded, or the windings may be loose. Before making any adjustments, inspect the transformer for signs of wear and tear. If the transformer is in poor condition, it may be necessary to replace it rather than attempt to adjust the taps. 14thly, measure the voltage of the equipment. After adjusting the transformer taps, measure the voltage at the equipment to ensure that it is within the acceptable range. Use a high-quality voltmeter to take accurate readings. If the voltage is still too low or too high, further adjustments may be necessary. 15thly, check the grounding system. Ensure that the grounding system is properly installed and maintained. A properly grounded system is essential for safety and helps to prevent electrical shock hazards. Check the grounding connections at the transformer, panel board, and equipment to ensure they are secure and free of corrosion. 16thly, consider energy efficiency. While boosting the voltage may improve the performance of the equipment, it may also increase energy consumption. Monitor the energy usage of the equipment after the adjustments to ensure that it is not excessive. If energy consumption increases significantly, Further adjustments may be necessary to optimize efficiency. 17thly, use appropriate safety equipment. When working with electrical equipment, always use appropriate safety equipment, including insulated gloves, safety glasses, and arc flash protection. Follow all safety procedures to prevent electrical shock and other hazards. 18thly, consider harmonic distortion. Adjusting the transformer taps can affect the level of harmonic distortion in the electrical system. Harmonic distortion can cause problems with sensitive electronic equipment and can also increase energy consumption. Use a harmonic analyzer to measure the level of harmonic distortion before and after the adjustments. If the distortion is excessive, mitigation measures may be necessary. 19thly, consider power factor correction. Adjusting the transformer taps can affect the power factor of the electrical system. A low power factor can increase energy consumption and reduce the capacity of the electrical system. Use a power factor meter to measure the power factor before and after the adjustment. If the power factor is low, power factor correction equipment may be necessary. 20thly, consider surge protection. Adjusting the transformer taps can affect the susceptibility of the electrical system to voltage surges. Voltage surges can damage sensitive electronic equipment. Install surge protection devices at the transformer, panel board, and equipment to protect against voltage surges. 21stly, consider load balancing. Ensure that the load is balanced across all three phases of the electrical system. An unbalanced load can cause voltage imbalances and can also reduce the capacity of the electrical system. Use an ammeter to measure the current in each phase. If the load is unbalanced, redistribute the load to balance the phases. 22ndly, consider the long-term effects. Adjusting the transformer taps can have long-term effects on the transformer and the electrical system. Monitor the transformer and the electrical system regularly to identify any potential problems. Perform regular maintenance to ensure that the transformer and the electrical system are operating properly. 23rdly, consider the cost. Adjusting the transformer taps may seem like a simple and inexpensive solution, but it is important to consider the long-term costs. The costs may include the cost of the electrician, the cost of the safety equipment, the cost of the monitoring equipment, and the cost of the maintenance. In some cases, it may be more cost-effective to replace the transformer with a new transformer that is properly sized for the load. 24thly, understand the transformer's nameplate data. The transformer's nameplate provides important information about the transformer, including its kVA rating, voltage ratings, impedance, and tap settings. Understand this information before making any adjustments. 25thly, verify the transformer's wiring connections. Ensure that the transformer's wiring connections are correct and secure. Loose or corroded connections can cause voltage drops and can also create a fire hazard. 26thly, consider the environmental conditions. The environmental conditions can affect the performance of the transformer. High temperatures, humidity, and corrosive atmospheres can degrade the transformer's insulation and windings. Protect the transformer from these environmental conditions to extend its lifespan. 27thly, consider the location of the transformer. The location of the transformer can affect its accessibility and safety. Locate the transformer in a well-ventilated area where it is easily accessible for maintenance and inspection. Ensure that the transformer is protected from physical damage and unauthorized access. 28thly, consider the type of transformer. Different types of transformers have different characteristics and limitations. Understand the type of transformer you are working with before making any adjustments. 29thly, consider the winding configuration. The winding configuration of the transformer can affect its voltage and current relationships. Understand the winding configuration before making any adjustments. 30thly, consider the impedance of the transformer. The impedance of the transformer can affect the voltage regulation and fault current levels. Understand the impedance before making any adjustments.